Does that show up okay?
Yes, it looks good.
Okay. Yeah, I'm going to talk about the operational forecasting of rapid intensification with an emphasis on the Hurricane Center. And this is a summary of an article the 4 co-authors here just published in the special issue of Atmosphere. It came out last month, so a lot of material is in that presentation. The outline is I'm going to give a little bit of a background. I'll be talking about the evaluation of the deterministic intensity models. Then we'll switch to John Kaplan. We'll talk about probabilistic intensity models, and James Frankin will discuss the new HFIP RI metric, and then also do the conclusions. So just as some background, this is the intensity forecast errors by decade. This is from a paper from John Cangialosi. You've probably seen this before. And the main thing I wanted to point out is that there was some incremental improvements by decade, but the biggest jump really occurred in the last 10 years. And I think that was mostly due to HFIP and the fact that the HWRF model now has skill and is basically the best intensity performer, along with COAMPS TC. And the secondary contribution was the implementation of consensus models. Now that there are several dynamical models that have intensity skill, and then the statistical models also have some skill. So combining those in optimal ways really led to the improvement. But I don't think we would have seen that jump without the improvements in HWRF. So that was a great accomplishment. But the purpose of this talk is to answer the question, has rapid intensification forecast also improved? Did we also see that big jump like we did in the basin-wide statistics? So I'm going to start by answering that question for the deterministic models. And I'm going to use probability of detection, false alarm ratio, and bias to answer that question, and to look at the performance of the available deterministic models back to the early 90s when they were first implemented for the Atlantic and the Pacific. And because of the fact that I'm using a pod and FAR, they tend to be unstable for small sample sizes, so the data is composite over 5-year intervals. In the NHC operations now, there's many definitions of rapid intensification that are used and they have guidance for. There's basically 8 different ones that are included in the ship's guidance. But I'm just going to concentrate on 3 of them. A 24-hour, 48-hour, and a 72-hour intensity change, the ones I have listed there at the bottom. So just to review, the probability of detection, that's the number of times that a model forecasted rapid intensification correctly, divided by the observed number of RI cases. That one is pretty straightforward. The false alarm ratio, sometimes that's defined in different ways, and sometimes it's called the false alarm rate, meaning different things. But the one I'm going to use is the one in textbooks that's called the false alarm ratio. And that's the number of times RI was forecast incorrectly, divided by the number of times it was forecast by a model. So it only includes information about the forecast, nothing about the verification. And then the bias is just the number of times rapid intensification was forecasted, divided by the number of times it occurred. And it doesn't matter whether you got it right or not. It's just to give you a bulk measure of whether a model is able to forecast RI at the proper rate. And the bias is 100% is the best. That means it's forecasting at the right rate. So simple example is if you had 10 forecasts, the ones in red, if you had 3 times the model forecast RI, and then the verification had 4 RI cases also indicated in red. In this example, 2 of the RI forecasts were correct, and there were 4 observed, so the pod would be 50% in this case. 1 of the RI forecasts was wrong, so that means 1 out of the 3 was incorrect, and that would give a FAR of a third, 33%. And the bias in this case, there were 3 times RI was forecasted, but it was observed 4 times, so the bias is 75%. And we loosely defined in writing this paper that if a model can detect at least some RI cases, and it's right more than half the time, we consider that model to be useful. If a model has high probability detection, but also is wrong more than half the time, it's not very useful to forecasters. So that's our rough definition of a useful model forecast. The models we included in the deterministic verification are listed here. Some of these go back to the early 90s. The two oldest ones are SHIPS and the GFDL model that were implemented. And we include statistical models, regional dynamical models, a global model, and some consensus. There were other aids around, but we didn't include those for various reasons. And most typically is that they were pretty much the same as something else, or the sample was too small to provide stable statistics. So for the 5-year periods, we chose one representative model for each of the 5 years of the 4 different types. The SHIPS model was available the whole time, so that we use SHIPS for every 5-year period. The regional models, kind of the first half of the sample is the interpolated GFDL, or the first couple of years there was no interpolation, so we just used the late model. And the second half of the sample is all HFIP. The global model is all GFS, or the early version in the early years. The late version in the early years. And then the 2 consensus models, equally weighted consensus, and then the corrected consensus HICA for the last of the 5-year periods. So some results, starting with the SHIPS model. If you look at the red lines there, this shows that SHIPS in the first 10 years never forecasted rapid intensification even once. I should point out that the points on this diagram are at the end of the 5-year periods. So like the 1995 point represents 91 through 95. It's only in recent years where you started to see SHIPS being able to detect a few of the IR cases for the Atlantic, but it still is pretty limited. For the Eastern Pacific, however, SHIPS actually can detect about 20% of the IR cases, even for the bigger thresholds. So it is starting to show some ability to forecast RI. The regional models is kind of an interesting story. I'm glad Morris Bender is on, because maybe he can back up some of the speculation that I'm going to make. But basically, when the GFDL was first implemented, it did actually detect RI about 20% of the time. But unfortunately, it had a false alarm ratio of 90%. So it almost always forecasted RI. And I think that was just because, it was a research model. It had parameterized convection. It didn't have ocean coupling initially. And so as they improved the model and put in some of these other features, actually the probability detection went way down. But after about 10 years of operational implementation, the 2001 through 2005, it actually started to show some utility, where you see here at least it's detecting 10 to 20% of the cases, and it's starting to get its false alarm ratio down. So it did actually make some headway. When the HFIP was implemented, these last 3 lines, you can kind of see fairly steady improvement from very low probability detection to, gradually improving, and then with the false alarm ratio coming down. So the last 5-year period, the HFIP model satisfies the condition for being a useful model for the Atlantic. East Pacific is actually kind of similar. You see that same behavior for a GFDL at the beginning, high false alarm ratios, but then gradual improvement through 2005. And for the HFIP, the last 3 points, the same kind of thing, where the last point here is starting to show some utility. The GFS and the consensus models, ICON and IBCN, almost never really forecast RI. The probability detections were really low. I think that was a resolution issue, and also the consensus included the SHIPS model and LGEM later, which hardly ever forecast RI. HICA, on the other hand, the corrected consensus had pretty decent probability of detection, especially in the East Pacific. And so using that, it does seem to have some utility directly for rapid intensification. So just to kind of conclude my part with where we are now with RI, this diagram shows the probability of detection on the x-axis, false alarm ratio on the y-axis, and you can kind of see that the pods are still pretty low. If you're up in this blue area, it means your FAR values are too big to be useful. But one thing that this shows, yeah, I just wanted to see Morris's comment there. One thing this does show is that there are quite a few models that are in this area where the forecast is useful. And the two best models were HFIP and HMON in the past 5 years for the Atlantic, with HICA kind of a close second. I also wanted to point out this red point. Some of us that were involved in the initial discussion of HFIP, we toyed with the idea of having one of the goals is to get the RI probability of detection to 90% with a false alarm ratio of 10%, and that's that red dot here. And so this diagram shows that we're really a long ways away from that. I don't think we actually adopted that as a formal metric, but I know we considered it. Maybe it's good that we didn't. Things are a little better for the East Pacific. You can kind of see these dots are moving closer to the red dot. And the two best performers were SHIP's model and HICA. So the statistical techniques seem to work better for RI prediction in the East Pacific, whereas the dynamical models work better in the Atlantic. And then finally, this just shows the bias of the NHC official forecast. So if this was 100%, that means that NHC is forecasting RI at the same rate that it occurred. And the Atlantic, there's kind of this steady kind of 20% value for the lowest threshold, although I didn't show it, but the false alarm ratios were really high at the beginning. But in more recent years, you start to see NHC actually does forecast even the higher thresholds of RI, and that's a new development. And for the East Pacific, it's the same thing, but it started sooner. That they actually predict the 30 knot in 24 hours at about 50% of the rate that it occurred. And one thing I did want to mention is that this blue dot here is for NHC, for the official forecast, and it's better than all of the deterministic guidance. And one of the reasons for that is they also had some probabilistic intensity guidance. And so, and John Kaplan's going to talk about that next. So go ahead, John, when you're ready.
Well, thanks, Mark. Yeah, so as Mark mentioned, I'm going to talk a little bit about the probabilistic models that have been introduced operationally starting back in 2001. Mark and I developed a simple statistical model to predict the probability of RI for the 30 knot and 24-hour threshold. And those we use mainly environmental predictors from the SHIP's model, which are GFS based. There were some improvements over time. I don't want to go through all of them, but we did introduce a more sophisticated model in 2006 based on discriminant analysis. And also, initially, the forecasts were only provided for the Atlantic Basin. We introduced a model for predicting those in the East Pacific as well, and some added intercore predictors were introduced, and we also added some RI thresholds at some higher thresholds and lower thresholds. A bigger advancement was made in 2016. We introduced an enhanced version of SHIP's RI with some additional predictors. Also, there were two new models based on logistic regression and Bayesian approaches that were developed by Chris Rozoff and Jim Cosson, and then the consensus, just the average of those. And then we introduced models for these different lead times, 12 hours, 36, 48, and 72 hours. And then finally, more recently, Matt Underlin developed a model, DTOPS. We'll talk a little bit more about that in a few slides, which is converting the deterministic intensity forecast from the regional models mainly to probabilistic models. Next slide, Mark. So a little bit, just the verification methodology we used. We only verified cases that remained over water in tropical or subtropical during the forecast period. The three main metrics were the bias, which is simply just the sum of the forecasted probabilities of RI divided by the observed. So a bias of 1 or a B sub P of 1 is a perfect forecast. There's no bias. The Breuer score is just the sum of the squared of differences between the observed probabilities of RI and the forecasted, where the observed is 0 if RI did not occur and 1 if it did. So Breuer score of 0 is a perfect forecast. And then for the Breuer skill score, we needed a reference model. And the reference model is climatology, where climatology uses the climatological rate of RI for a given threshold and basin. And that's compared to the model forecasted RI. So for each case, whatever the climatological rate is, it's like 0.06% in the Atlantic. That was used for every case. Next slide. So this is just the results for the last 20 years for the Atlantic on the left, East Pacific on the right. The blue line is the 25 knot and 24-hour threshold, and the 30 knot and 24 is in red. The Breuer skill score is on the y-axis, and this is the year on the x-axis. And what you can see is that there was some skill at the 25 knot threshold in the Atlantic initially, but we had a rough patch here in the middle time when it was a fairly inactive period, and there were a couple of years where there was 1 RI case each year and one year where there was 0. And it's hard to beat climatological rate of 0.06%. When you're forecasting. And there was a bit of a bias, there's still a bit of a bias, but particularly back then. But in recent years, the models have improved quite a bit, and there's now some modest skill, well, low to modest, I guess, in the Atlantic, about 15 to 20%. And in the East Pac, there was consistent skill basically for the whole time period, and it has improved with time, and now it's basically between 20 and 25%. Mark, next slide. This just shows the results for the last 5 years when those new models were introduced and the skill became a little bit more consistent. And this is again the Breuer skill score on the y-axis, and on the bottom this is the different RI thresholds. There are 8 of them, a lot of them here, and there are a lot of bars. The red bars are the ship's RI forecast. The logistic regression is in green, the Bayesian in blue, and the consensus is in this orangish color. And there's a lot of bars here, so I don't expect you, I'm not going to go through each one of them, but the bottom line is that there was skill for all the models in each basin at each threshold, with save for maybe one in the East Pacific for one model. And the skill in the East Pacific clearly exceeds that of in the Atlantic at each RI threshold. And it's interesting that sort of at the middle time frame, middle lead times, and the skill is actually comparable, especially for the ship's RI, than it was at the shorter lead time. So maybe the environmental information is that's the best time period that it can provide skill. Mark, next slide. This is just a reliability diagram for those same models, same color schemes, Atlantic on the left, East Pacific on the right. I should mention this is for the RI threshold, 30 knots in 24 hours. This is the one with the longest time period, and also just to be consistent, we wanted to focus on that in the more recent time period as well. And what you can see is that the reliability is fair. A perfect reliability is this the black solid line diagonal going from the lower left to the top right. And you can see higher probabilities in general were more likely to be observed to be high, but obviously there's quite a bit of noise in there as well. I guess the most notable result, I think, is that the high probabilities are very hard to forecast. They're not forecast very often. This is refinement distribution here, just a percentage of cases at a given that are forecast for a given probability, and they're quite low. They're higher in the East Pac, even though they're lower, and that's why you get higher skill. So it's just very hard to predict definitively that RI is going to occur, which is probably not a surprise to anyone on this call. Next slide, Mark. This is just kind of a summary of the bias of those models for that period, again, for 30 knot and 24 hours, that B sub P value that I discussed earlier. And again, the bias of 1 indicates, a B sub P of 1 indicates there's no bias. And the ship's RI tends to have a high bias, but I should have pointed out that those are mainly for the lower probability forecasts. It tends to over forecast at low probabilities and actually under forecast at the higher ones, especially in the Atlantic. So anyway, the best, by this metric, the best model was a logistic regression. And consensus, which kind of averages out, the Bayesian was kind of low and the SHIP was kind of high, so it averages out to consensus works better. That's where the higher skill comes from the consensus, which I hopefully mentioned, but I might have forgotten. Consensus in general had the most skill of the three models. When you average those three, that exceeded the skill of any individual model. Next slide, Mark. Just a little bit about the DTOPS model. This is Matt Underland's model, basically. So I'm just going to do my best to summarize, and Mark knows a lot more about it, and Matt if he's on. So basically, as Mark discussed, that the increased skill of deterministic models that's been observed in recent times seemed like a good idea to try and maybe use that information in a probabilistic way. And so they created this new model called DTOPS, which is a deterministic to probabilistic statistical model based on logistic regression. And the predictors used were the max wind change forecast from the HWRF, GFSI, LGEM, and CHIPS, and then the minimum pressure change from the ECMWF model, as well as the initial intensity, cosine latitude, and then there's some nonlinear predictors as well. And the probabilities provided were the same as the RI threshold, and this was implemented in 2018 operations for the Atlantic. Next slide, Mark. This is just the skill diagram similar to one I showed a few slides ago. This is for the 2018 to 2020 period, homogeneous, just as the other slides I showed with the other verification of the different models. So the SHIP's RI models are the same as before, and the DTOPS is in pink. And you can see in the Atlantic that the skill was at least as good generally as the SHIP's RI models, and it was clearly better in the EastPac, particularly at the lower threshold. This is really good skill here, 35%. That's tough to beat, and also at the longer range. So there's clearly a lot of hope there, but by using the forecast from the deterministic models, I think that's encouraging. And that's all I have, Mark.
Okay, thanks, John, and James will take it from here.
All right. So we've looked at the performance of some of the models, deterministic and probabilistic. We wanted to take a look also at the historical performance of our current HFIP baseline. And if you recall, a couple of years ago, we decided on a fairly simple programmatic baseline that could be easily communicated to people, non-scientist types. So we wanted to stay away from things like POD and FAR and Breyer's skill score and things like that. So we chose the simple mean absolute error of the IVCN consensus. We report on that kind of metric all the time in the NHC verification reports. In order to get a decent sample, we were going to combine the Atlantic and East Pacific basins. And we defined a baseline period of 3 years, 2015 to 2017. And the decision was made to then evaluate IVCN only at those times when RI was either ongoing or forecast by one or more of the members of the consensus. And the idea was to get not only those cases when RI occurred in the atmosphere, but the flip side of that when forecasts of RI were also made. So you didn't bias the metric towards the more aggressive models. Other than those rules, the standard NHC verification rules would apply, and the IVCN consensus for that baseline period, the composition there was shown. It was decay SHIPs, LGEM, the GFDL, the HWRF, and COAMPS TC. And the HFIP goal, which I think we'll see in a few minutes, maybe isn't all that unreasonable, is to reduce the intensity forecast guidance errors by 50% for the RI events. So next slide, Mark. And so I think most people have seen this before. This is just the values of what that metric turned out to be. The baseline errors are basically between 25 and 35 knots from 24 hours on out to 5 days, meaning the targets are roughly 15 knots, which is a big enough number that it could actually be measured. We know that the uncertainty in the best track intensity is perhaps about 10%, but you could actually tell if you were hitting a target that was 15 knots. So that was kind of nice. Next slide. So in order to go back and evaluate how this metric did historically, we had to go back and reconstruct some intensity consensus. Actually, the first use of ICON at NHC was in 2006. So for the years 2001 to 2005, we formulated the closest available consensus, decay ships, and the interpolated GFDI model. And so you can see it's actually kind of interesting how the consensus changed over the years. Beginning in 2008, it expanded from 2 models to 5, and we've basically had 4 or 5 models in the consensus, ever since 2008. Some of the things that happened over the years was the dropping out of the GFDL after 2016, adding of COAMPS TC in 2016, and then the past 3 years, the addition of HMON to the consensus. Next slide. So we went back and we looked at combining the Atlantic and East Pacific basins together. Again, this is all of the cases when RI was either observed or forecast by any of the members of the consensus. And the errors plotted at 24, 48, and 72 hours back from 2001 to the most recent year. Trend lines are shown in the dashed lines. A couple of things to point out. Number one, this diagram is noisy because even when you combine the basins, you don't get really large sample sizes. So I forget the year, but one of these 72-hour points only has 2 cases in it, and the most number of 72-hour cases is 43. So these are small cases. The trend lines are downward at 48 and 72. It's interesting that the 24-hour trend line is kind of flat. The first 4 or 5 years had some pretty low errors in the consensus. I'm not entirely certain why those errors there were so low. It's possible that there weren't as extreme examples of RI in that period, but we haven't really looked at that. More interesting, though, I think, is the fact that you look at the last 3 years after we got out of the baseline period, 2015 to 17, and we've had 3 really good years in a row. And if you compare the 2018 to 2020 errors, the last 3 years, to the previous 3, which is the baseline period, we've cut the errors down by 27% at 24 hours and roughly 20% in 48 at 72. So, maybe that 50% reduction in the goal of a 50% reduction rather wasn't an unrealistic goal, because it looks like we're well on our way. Next slide. It's interesting to compare the consensus errors for the RI events, which is the diagram on the left. It's the same one that was on the preceding slide, with all the cases, all the forecast, which is on the right-hand side. And so obviously, when you look at all the cases, the errors are much lower. You've got a lot of cases, so there's not much noise there. But if you dig into that, you can't really see it visually, but if you go and look at what the improvement rates are for the RI cases on the left and the total cases on the right, the improvement rates for RI, at least at 48 and 72, are about 1% a year. Whereas for the overall sample, it's about 2% a year. So the improvement rates for RI are slower than improvement rates for intensification as a whole. Next slide. You can also compare the IVCN with the official RI errors. Again, the sample is would be when the official forecast when RI either occurred or was forecast by the official forecast. And so a couple things to note when you compare these two diagrams is, first of all, the official RI forecasts have less variance from year to year. It's not surprising since the models can bounce around. The official forecast tries not to bounce around so much. But particularly if you look at the very right-hand side, the last few years, the official errors are a little bit lower than the errors from IBCN. So that's suggesting that today's forecasters are adding value to IBCN either through their own expertise. For example, a forecaster can look at the structure of a storm and make judgments about whether it's ready to undergo RI, or the forecaster also has these additional tools that John talked about with the DTOPS and the SHIPS RI index, beyond what's available in IBCN. Next slide. And so with that, I think we'll just recap a couple of highlights here. Mark talked about the fact that the deterministic guidance really only recently has showed forecast utility for RI. John then talked about the probabilistic models. I think the big takeaway there is that there were major upgrades in the last 5 years that have finally produced some consistent skill. The addition of DTOPS really upped the game in terms of the amount of skill we're getting from the probabilistic guidance. And it really looks like those products are contributing to the NHC official forecast. And then lastly, the fact that in the 3 years since the HFIP baseline was established, we've made good progress in the subsequent 3 years and appear to be well on the way to meeting that HFIP goal of a 50% improvement. And so I guess we'll stop there.
Thank you for the presentation. Now